forget the recording. Last time we introduced the concept of indices, indices for a large population, the incidence index, and an index for a small, confined, limited population that we call the likelihood index. This is one way of assigning a risk level and a safety level to different human activities in general. And in that case, we didn't use much other than some neat algebra about the definition of the log, the log to the base 10, the logarithm to the base 10 that describes systems in magnitude in decades or factors of 10. Thank you. So that's one method of estimating the level of safety or the level of risk. It has been adopted widely in situations like you read about or hear about, like the Richter scale to assess the intensity and the damage that can happen from earthquakes, and from maybe the Torino scale or the Fujita scale. But that's a scale that would go from 0 to 10 rather than an arbitrary number, 12 or 15 levels in the different scales. So you can apply this concept to situations that I gave you examples of, like in terms of a large population or a limited population. All right, so today we are going, since we are dealing with risk, we would like to be able to deal with what are the conditions under which we can say that risk applies or becomes feasible. And it is not just a matter of math or writing, getting some kind of numbers in a table. It has implications from the perspective of professional ethics and professional conduct. And notice that safety analysis and risk assessment is an activity at the service of society, or a public servant. So here today, we cover the condition under which we can say that risk does exist. It's very important because ethically and professionally, we would be faced with that situation when we make opinions, create opinions about risk in general. Notice that risk is associated, that's the first important aspect of risk. It's always associated with uncertainty. Uncertainty would be codified later on in a quantitative way in terms of the underlying mathematical background of either a Boolean algebra or a De Morgan algebra. But one condition for the existence of risk, as we are going to describe it today, is the existence of uncertainty. There are other conditions too, like the anonymity of the people who are subjected to risk and so on. However, the ideas of uncertainty have been introduced in many different ways historically, and by our understanding the history, we can understand really when is it that risk exists or does not exist. And we'll make the point that risk only exists in an anticipatory, like you are expecting something undesirable to happen, or a predictive stage, another way of saying anticipatory. Once the event that you are worried about occurs, it is not risk anymore. It is an accident. For instance, when we take airplanes for travel, there is a risk. The airplane can fall off the sky and we are gone. So as long as the risk is anticipated or is predicted, it is risk. If an accident happened to the airplane, it is not risk anymore. So the risk has some kind of properties of uncertainty, of realization, of anonymity that we have to associate with risk. If they're not associated with risk, it is not risk. It's some kind of frequency that people have written, and professionally you cannot say that it is risk. As I said, there is a historical kind of background dating back to the Middle Ages about that concept of uncertainty. And this is a poet and philosopher. His name was Ibn Yamin, and he classified humans according to their level of knowledge. It's a fun thing to read here. So he classified humans as, quote, one who knows and knows what he knows, his horse of wisdom will reach the skies. One who knows but does not know what he knows, he is fast asleep, so you should wake him up. One who does not know but knows what he does not know, his limping mule will eventually get him home, because the mule knows where the stable is. And one who does not know and does not know what he does not know, he will be eternally lost in his hopeless oblivion. So hopefully we are all of the first category, because otherwise we are bound into oblivion according to the last category. Ibn Yamin was born in a family of a scholar and poet, another poet, Amir Yamin al-Din. He was a court poet of the Serbidar dynasty in the mid-14th century. Over 5,000 of his poems, mainly aphorisms, have been preserved, including what's called qasida in Arabic and masnawis of a philosophical and mystical nature. You notice that that type of a culture eventually found its way to Europe and got Europe out of the dark ages. Something very interesting now, an unknown poet repeated the feat of Ibn Yamin in a collections of poems based on speeches by United States Secretary of Defense Donald Rumsfeld. He calls it Pieces of Intelligence. The author is Hart Seeley. When Donald Rumsfeld was Secretary of Defense, that was the time of the war, the first war in the Gulf on Iraq. So he was very literate. He knew about that poem that we just read. So that is what Hart Seeley describes what Mr. Donald Rumsfeld said. Quote, as we know, there are known knowns. There are things we know we know. We also know there are known unknowns. That is to say, we know there are some things that we do not know, but there are also unknown unknowns, the ones we do not know, we do not know. And finally, there are unknown knowns, the knowns we do not want to know. So this is there is an element of fun, but it's primarily sarcasm about people thinking that they know about something but they don't know. So this is a concept of uncertainty. And life by itself, most of the variables that we measure, the speed of a car, of a rocket, the rate of death from different medications and so on, have an uncertainty in them. Whenever there is uncertainty, we have risk. So the known unknowns are the things we are aware of, but cannot fathom, or in another word, oh, this is the risk. So what he says here, known unknowns, is what we designate as risk in general. And it tells us another interesting aspect of risk here is that there is, it is always associated with uncertainty. Can you please sign your name here? All right, some other gentlemen, authors and philosophers, Alistair Crowell and Benjamin Yoskovich, wrote a book, Lean Analytics. You heard about analytics as a field of mathematics or engineering. They describe different ways of looking at data and the four knowledge categories. Again, we go back to known knowns. This is what in a different context we call facts. And you use analytics data to check those facts against them. And that's part of the field, of course, of statistics and probability theory. What they call in their poems known unknowns, this is what we described in math as hypotheses. They can be confirmed or rejected with measurements. So we make a hypothesis and we take measurements. The measurements, if they conform to the hypothesis, we accept it as a fact. there are unknown knowns. This is basically our intuitions and prejudices. Some people would enjoy bungee cord jumping, and some people say, no, I will never do that. This is too risky. So that's a subjective kind of opinion, and these are unknown knowns. So this can be put aside if we trust the data instead. And then we have the unknown unknowns that those poets have talked about, including our famous Secretary of State, Donald Rumsfeld. Those unknown unknowns can be just anything. And they're often left behind. We ignore them. We sweep them under the rug, in fact, but can be the source of great insight. So by exploring the data in an open-minded way, we can recognize patterns and hidden behavior that might point to opportunities in that case. So what are the objectives then of risk assessment, which is not the unknown unknowns or the unknown knowns? It's really, we are dealing here with the known unknowns. You'll find in that case that we have developed a methodology in mathematics to deal with that concept. And there are different philosophies and different approaches. We have to learn about the different approaches, and depending on the context that we are dealing with in science and engineering, we adopt the methodology or the approach that we think is best suited for what we are trying to do. So the objective of the risk, which is that part that we can identify as known unknowns. I'm translating what the poets and the philosophers have talking about into some solid, objective, quantitative engineering and scientific approach. So the known unknowns is basically what we call the risk assessment methodology. We can identify that the objectives are 4 of them. You want to identify, and we'll expand on this quite a bit later on, what are the initiating events that lead to the existence of risk. And for instance, if you look at the accident at Fukushima, what was the initiating event? Okay, let's keep you awake at 3 in the afternoon. What was the initiating event of the Fukushima accident as you read in the literature or the papers? Who's gonna tell us? Yes, the earthquake, right? So that was a natural event that was the initiating event. But usually initiating events do not just cause accidents. You'll find that an initiating event, and we'll quantify this later on, is always followed by another sequence of events that can turn the initial initiating event into something very serious. So for instance, after the Fukushima incident, there was a tsunami. All right, that's the second part of the sequence. After the tsunami, the water flooded the basement of the power plants, 4 of them. And again, that's another sequence. There was a flooding accident. Then later on, the electricity was lost. All right, so it was a station blackout, as we'll describe it later on. Station blackout led to the heating of the fuel in the reactors, and they had no power to cool it. So the fuel melted up, and so on and so on. So accidents in general have an initiating event followed by a sequence of other events. And we suggested that, say, for the space shuttle, it could be an equipment failure, or it could be a human error. So we need to cover all these sequences in general. Once you identify the initiating event and the event sequence, you try to provide realistic quantitative measures of the likelihood of the risk contributors. How often do you think they happen? For instance, the earthquake, how often does it happen? You go to the historical data and you discover, say, that an earthquake on the Richter scale of 9 or 8 happened in the last 100 years. So this is the likelihood of the risk contributors in that case. Third step is to provide an evaluation or a quantification of the potential consequences associated with hypothetical accident sequences. We create sequences that may not have occurred or may never occur, but as engineers, we assume that we know about how the system behaves, and that would be the process of fault tree analysis and event tree analysis that we learn later on. And then once you do this, you provide a reasonable risk-based framework for making decisions regarding ideological objects such as planes, refineries, nuclear power plant designs, operation, and siting. You'll find that this part here, number 4, is a different field of engineering and science. 1, 2, 3 is what we'll try to cover in our course. 4 becomes a different field. Now, here we assess the risk, we identify the risk. That's why we call it PRA. PRA stands for probabilistic risk assessment. This 4 here becomes risk management, which is another field of science and engineering, part of what we call system analysis or operations research. All right, so let's go on. We defined already the risk as the probability of occurrence of an undesirable event, P, small p here, multiplied by the consequences of that event. We expanded that notion to technological risk. So in that case, we added that summation sign over all the possible sequences of events. Each one has its own probability and its own consequence, and sum them over all the different sequences that a risky event or an accident can occur. This definition is fine for some applications. In fact, we'll use it in some applications, but you notice here that the risk now, since the probability in mathematics has no units, unitless, so the risk would adopt basically the same units as the consequence. So if it is loss of life per person per year, or it is like millions of dollars lost in a stock market crash, that it applies to all fields of engineering and science in general. However, that determination here may be a little unacceptable, because in that case, you'll find that the risk from a large number of small accidents would be the same as from a small number of large accidents. So for instance, if you have a large accident, P sub I would be large, the probability is large, but the results of the accident, the consequences are small. However, you can have a small number of large accidents, small accidents with a large consequence, and the total risk would be the same. So it is basically in that we have an assumption inherent in our definition here, is that the perceived risk of a large accident is greater than the equivalent risk from many small accidents because of human nature and the emphasis of our news media on the unusual newsworthy events. So let's take an accident that, for instance, causes that has a low probability, say an airplane crash. It has a very low probability, but the consequences can be large. You lose maybe 200 lives. But on the other hand, you'll find that car accidents maybe can cause the death of one person, the consequence, but they occur, in fact, with a very large probability. Yet you can calculate it and find that the same total risk is the same. I give you another example here, actually, a numerical example. If we get about 50,000 traffic accidents per year, that is true. It is not very much newsworthy. You don't read about it in the news media. That's not shown on TV, but they do occur every day. But they have a large number, so their probability is high, but their consequence is basically one single accident killing 50,000 persons would be very newsworthy. So it introduces what we call non-linearity into the process of risk assessment. So comes the Nuclear Regulatory Commission and suggests a modification of the equation that we wrote for the technological risk equation. So they take the consequence here and raise it to some power. And in that case, this is not linear anymore. It's not like a straight line. It is non-linear. And that nu here, that's Greek nu, usually is larger than 1, is a number that is introduced to account for the effects of perception. Humans have different levels of perception towards undesirable events. A value of 1.2 for nu here has been suggested in the United States by the Nuclear Regulatory Commission. So you can use the initial equation here. If you want to be more sophisticated, you take that nu if you are dealing with a nuclear reactor accident. This idea of perception can be eliminated if we look at risk in a different way. The different way is that we can consider risk as an ordered pair, not just P sub I, C sub I, but an ordered pair of probabilities and associated consequences in general. And basically, the consequences could be fatalities, could be morbidities, maybe people getting sick. Coal miners, for instance, get black lung disease. Farmer gets silicosis from dust getting into their lungs, and uranium miners would get, of course, cancer of the lungs from inhaling polonium-210 and lead-210 from the decay of radon in the mines. So in that case, what we do here is that we generate a composite risk curve where P multiplied into C, since they are a pair, multiplied into each other is equal to some constant K. And in that case, you find that you have a graph that goes like from the X and Y axis simply in a line that comes down. So in that case, it becomes a straight line if a log-log scale is used, and it is really a curve, P multiplied into C is equal to K. One must note there are uncertainties associated with both the probability P sub I and the consequences C sub I. The uncertainties are presented sometimes as Gaussian, normal, or bell-shaped curve. This is the same curve that you have seen in your classes when you took the mean value of experiments, taking the readings, and then associating them with a standard deviation in general. And in that case, these distributions can take a different name. Sometimes we call it a probability distribution, or we use that in one of the previous chapters. And the probability distribution usually is associated with discrete values when the numbers are like they add up to 1, but they are discrete values. We call them probability density functions when they are continuous variables. So we'll show that later on as we proceed more into the theory. Or some people simply call it a distribution to refer to either the probability distribution or the probability density function. All right, so let us, if we take risk and consequences as a pair, let us now get a primary definition of the risk, and that is based on probability theory. Now, each one of you may find themselves taking a full course on probability theory, depending on how interested you are in the ideas that we are covering here. But we'll cover as much probability theory, possibility theory, so that we can associate it with risk. Let us formally then define risk, all right? So we assume of the existence of n potential outcomes. So this is a symbol in math for all values of I, taking the value 1, 2, 3, 4, 5, up to n, to make it general right here. And for each potential outcome, O sub 1, O sub 1, O2, O3, O sub I, there is an associated likelihood. That's why I'm calling it L1, L2, L sub I. So O sub I is the outcome I and the likelihood of I. This is a formal definition of risk, a set of outcomes, O sub I, associated with a likelihood, L sub I. Let's take an example from probability theory of a risk, and you'll be astonished that the example is very simple here. Risk is, if we talk about probability theory, you are talking about random variables. And one of the random variables that we all know about is the process of flipping a coin. So if you flip the coin, you have an outcome, O1. What's O1? H, you get a head. Or the outcome 2, you get a tail. Or let us assume just that it also may fall on its edge. So I call that outcome E. Now for each one of those possible outcomes, O1, O2, and O3, we have associated a likelihood. What's the likelihood of getting a head? Oh, it's 1/2. What's the likelihood of getting a tail? Oh, it's 1/2. What's the likelihood of getting an edge? By experimenting with coins, you will never get a coin to fall on its edge. So we associate a likelihood of 0. So in that case, you'll find that the random variable of flipping of coin is basically a risk process. You risk getting a head or get a tail, and in some cases, people would flip a coin to decide on very major decisions in general. All right, let's take another example, the example of throwing a die. If you throw a die, you have different outcomes too. You can get a 1, you can get a 2, you can get a 3, a 4, a 5, and a 6. With each outcome, we have associated, we can say associated a likelihood. 1/6 of the time, if you repeat the experiment 1,000,000 times, and we might be able to actually simulate the throwing of a die or a coin on a computer, and I'll show you how this is done using what's called Monte Carlo techniques, or the Monte Carlo method. So you have 1/6, 1/6, 1/6, 1/6, 1/6, 1/6 as the likelihoods, and it identifies the process of throwing a die as basically a risk distribution. Again, it's a random variable. Why is it random? Because you don't know when you throw a die or you flip a coin whether you'll get a head or a tail, or 1 or a 3 or a 6. The outcome is not kind of can be predicted, but 3 times but, there is an associated probability distribution if you repeat the experiment a large number of times. So definitely half the time you'll get a head, and half the time you get a tail in flipping a coin, and 1/6 of the time, if you repeat the throwing of the die a very large number of times, you cannot say I'm going to get a 3, the 2, or the 1, or the 6 beforehand, but you know that there is an underlying probability mathematical distribution. You get it as a 1/6, 1/6, 1/6, 1/6, 1/6. Now those two distributions are discrete values, because you see you get 1/2, 1/2, 1/6, 1/6. But if it is a continuous function, we call it a probability density function. When it is discrete, we call it a probability distribution. That's some kind of accepted from the fields of statistics and probability theory. Another example, it doesn't apply just in flipping coins or throwing a die, the weather forecast, and you can think about many other random variables that basically we deal with everyday's life. Every day, for instance, we leave home and we decide whether we take an umbrella or not take an umbrella, get a coat on or not take a coat on, depending on the temperature. The weather forecast could be simply either a clear sky, that's O1, the outcome number 1, or that it's going to rain. And the weather forecaster tells us, there is a 30% chance, in that case, the probability is 0.3, and that it is going to rain, and 70% the likelihood is for us to get a clear sky. Accordingly, we take many life decisions on an everyday basis based on this idea of estimating risk. All right, we'll expand on this later on in terms of random variables and the uncertainty, types of uncertainty. There are uncertainties that are associated with numbers. We call these random variables. And there are uncertainties associating with the meaning that we give to our measurement or our data, like temperature is a random variable because it's a measurable quantity. Hot, cold, tepid is a meaning that we associate with the data, the measurement. This is what we are going to call a fuzzy variable, and then we'll find ways of combining them together to get better knowledge about the uncertainties in the world. All right, along this line, we suggested now that this is a probability distribution because it's discrete variables. What if the distribution is a continuous curve? So we learned something here today that we are going to call the risk curve or the risk profile, and it will have very interesting applications. It was invented in the context of nuclear reactor accidents. That's why the course really emphasizes reactor accidents, because the risk assessment field was really developed lately in the last 30, 40 years in the context of nuclear reactor accidents. So in that case, you'll find that one gentleman named Farmer suggested to us the Farmer curve, not the farmers themselves, but the name of the person is Farmer. All right, so let us think about the continuous distribution, anything that's a function of a variable X. X could be some temperature, say the fuel in a nuclear reactor. It could be a flow rate of a pump. It could be the speed of a car, any variable that we measure. If it is a continuous function, we don't call it a probability. We don't call it this distribution. We gave it the name of PDF. Try to remember that PDF if you didn't have classes in probability theory, and that stands for probability density function. Now, the probability density function, if you integrate it from minus infinity to a value of X, we like to call it the cumulative distribution function. And let me clarify this. So you'll find that here it is now. We are dealing with a continuous function. And let's take it like something like a normal distribution, as you have seen it in many other classes. That is of X here, and this is f of X. The condition for calling it a probability density function, PDF, is that the integral of f of X dx over the range of integration. It can come from minus infinity here, but in fact, it is not defined there. So it's 0. So you start from 0 to infinity. In that case, that should be equal to 1. What do we call that condition here? Anybody from who has had knowledge of probability theory? Yeah, that's a normalization condition. Okay, now we suggested that this applies to any probability distribution, like flipping the coin, 1/2 plus 1/2 adds up to 1, right? Throwing a die, 1 6 1 6 1 6 1 6 1 6 and 1 6 add up also to 1. So in that case, for a continuous distribution, the f of X dx should be equal to 1. Now, suppose that I'm interested in what is the probability, and the probability is equal to 1, meaning whatever event you're looking at is going to happen because we are integrating over the whole curve. However, if you integrate only up to a point here that we are going to call small x, all right, then it is not a probability density function anymore. It's called the cumulative distribution function. So in that case, it's the integral from 0 here, the beginning, to the point x, meaning that area only here, up to x only of that f of X dx. And you'll apply that today to a very simple distribution, the negative exponential. In that case, you'll find that because when you integrate this one here, you get another function. And that's why it's a cumulative distribution function. Cumulative in which way? Because we are integrating that area right here up to some point x. Say that point x is 10, and say this is a number of deaths from some kind of an accident. So that area here would be the probability of the occurrence of x below the value of 10. And we call this the cumulative distribution function. So if I want to estimate, for instance, I'm investing in the stock market, and I want to make sure that I don't lose more than $1 million. So my cumulative distribution function should be less or equal to $10 million. Otherwise, I am going to lose all the $1 million. So in that case, the cumulative distribution function becomes an important parameter for the value less or equal to the value that I am giving on the graph. Now, suppose that you want to think in a different way. You want to think that, say, the income that I get from my investment should be larger than $1 million. So in that case, if it's larger, you are looking at that area right here. See, it's larger than X. So in that case, we define the 1 minus the cumulative distribution function, because the area here is all 1 minus the small area here, less than X, as basically the integral for, well, just write it as 1 minus the cumulative distribution function. All right, so this is the simple math that we need to remember. I think you may have met that already in some other courses. The cumulative distribution function is designated with the capital F. Usually we like to write small f for the function that we are considering, capital F with the cumulative distribution function. And this becomes the probability of the outcome that we are dealing with being less or equal, I can say here, to X. Now, 1 minus the cumulative distribution function is basically what we call the complementary cumulative distribution function. So these are 3 definitions that we learned today, and I'm going to ask you to work on a problem along this line. Once you work on a problem, a very simple function, the exponential function, for instance, you'll find that it is very simple to understand. Calculate the probabilities under different conditions. So we have the probability density function. It normalizes to 1, meaning that the event is going to happen with probability 1. It's certain to happen when its probability is 1. The cumulative distribution function is 1 minus the cumulative distribution function is an integral up to X, and then anything beyond or above X is designated as F, maybe the bar here, F of X, which is 1 minus F of X, which you can write as 1 minus the cumulative distribution function, which you can say, all right, it's really the integral from X to infinity of the probability density function. And this idea of the complementary cumulative distribution function is the basis of what is called the Farmer curves. And the Farmer curves is a standard way in probability theory in describing the risk. That Farmer's curve are basically complementary cumulative distribution function. They look at that side of the normal distribution above a given value. So we are calculating the value, say, of the loss of property or loss of life to be more than X. Say that hurricane, say Sandy, have caused more than 1,000 people deaths. That is the integral from 1,000 up to infinity on the normal distribution in general. So the example would be on the horizontal axis, could display on our graph here on the board, the accident severity or the number of fatalities, as I suggested. And the vertical axis would show the frequency of fatalities exceeding a given number X. Because it exceeds the X on the distribution, it is a complementary cumulative distribution function. So remember that, probability density function, cumulative distribution function, complementary cumulative distribution function. One should note that the fatalities usually start at the value of unity, even though I wrote it formally as from minus infinity. But since the function is not defined below 0, it makes no sense to integrate below 0. And the inclusion of a 0 fatality in the Farmer curve requires a display of an unreasonably wide range of likelihood, especially if a logarithmic curve is used. And when you take the logarithm of the value of 0, you get minus infinity. So programming it, putting it on a computer will give you a fatal error in that case. So here we depend then on the formal definition of risk that we have today as being represented either by a discrete distribution, we call it a probability distribution or distribution, it's in a simple way. and the concept of a probability density function when it is continuous. And Mr. Farmer developed the idea, and it was set up in what we mentioned earlier, the probability of nuclear accidents causing loss of life, or basically morbidity. Morbidity means making people sick through radiation, and he published it as part of the reactor safety study, the WASH 400. That was the first study ever about the risk of using nuclear power plants. So this is a Farmer curve, for instance, because it was applied in that range of having 100 nuclear power plants, early fatalities. And notice, let me go back to the graph here, that if I take that graph and try to estimate that f of x dx, and basically show the cumulative distribution function, you can take notes about this. You start integrating up to the value of x. So as you integrate, you start with a 0, 0. Oh, well, eventually your curve here reaches the value of 1. So you'll find that the cumulative distribution function takes the shape of a sigmoid. We call that a sigmoid. The complementary cumulative distribution function is 1 minus the cumulative distribution function. So you'll find it coming in here and from the value of 1, and then ending up with 0. And that comes from the integration of the probability density function. I showed here the normal distribution, but I'll give you today a problem for an easier function, which is the exponential function. The exponential function would start from 0, and let's take it at k e to the minus kx. And this is x. When you integrate it, you'll find that you still get the same kind of shape. You start here with the area being 0. As you keep integrating, you'll find that, eventually you get to the value under the curve here, which is 1 at infinity. And the complementary cumulative distribution function will come in a curve like this. Hence, you could see there on the graphs by Mr. Farmer that he calculated as a description of the risk. He is calculating here the complementary cumulative distribution function. And notice here on his x-axis, he's estimating the number of fatalities from having, say, 100 nuclear power plants operating in the United States. And then he shows this against the annual frequency of fatalities exceeding x, or larger than x on our normal distribution. And you could see here that the probability of having the number of fatalities exceeding 10 is something in the range of, let's say, 5 10 to the minus 5, or 5 in 100,000. And then you could see that the fatalities exceeding 1,000 becomes much less, 10 to the minus 6. That's very obvious. Now, the idea here was to compare the risk from nuclear power generation. That's how this Farmer curves idea was invented, against other risks that society meets in our technological civilization. So you could see here that he generated the complementary cumulative distribution function. Let's call it the Farmer curve now, since we know about it, from fires. You could see that there is 10 or 4 order of magnitude difference in the risk between having 100 nuclear power plants operating in the United States causing fatalities, and fires that occur in the United States. So they're caused by humans. Most of the fires in homes in the United States starts around Christmas, when people would basically become complacent in heating their Christmas trees. At some point, they used to have even candles, but now there are lights. Those lights can start a fire, or they can have an electric heater flip down on the ground and start a fire. He also generated the risk from explosions causing deaths, chlorine releases from maybe train carrying cars filled with chlorine, flipping over the railroad. And here another one, air crashes, the risks that society gets from air crashes every year. And these are people who die as well on the ground, as well on the airplane. And this is the risk from air crashes. So you notice here that he concludes basically that 100 nuclear power plants risk is less than all these societal risks that we are subject to. And in that case, you find that the total man-caused risk is much higher by about 4 orders of magnitude. So in that case, we can convince people as engineers if indeed we have a risk in a technology that is much less than what we incur from natural or other societal risks that we take. So you find again that this is the end part of that risk assessment, as I suggested. And some people suggest maybe, oh no, this risk is too high. So as engineers, we are bound by ethics and professionalism to abide by what society wants from us. So we can go and increase the safety level of the designs that we make for cars and airplanes and any engineering system to the level that society wants us to have. For instance, let's talk about the risk in car accidents in general. If you go to cars that were built before the 1950s, you will not find, for instance, seat belts. I used to have a very old car as an antique, and I had to buy seat belts. How much would the seat belts cost me? Can you guess a number, please? Yeah, anyone? How much? $200, actually. It's very cheap to add a seat belt to a car. I'm giving that example because we are going to come to it later on. Suppose that the car seats is not enough to make me feel safe. So we added another feature to our vehicles, to our cars, which is, what is a higher level of safety in cars? Before airbags, anti-lock brakes, right? Anti-lock brakes cost us $800. Then we come to your airbags. That's at least $1,000 or $2,000. This would be for the driver airbag. Oh, but some people say, oh, that's not enough. Let's also have passenger airbags. And then we have side airbags. And then we add a camera in the back of the car so that people, and this is an accident that actually happened. Unfortunately, people run over their kids by backing up on their driveway when their kids are behind them without seeing them. So every time we add a safety feature here, you notice that we have to spend a larger amount of money. So the reduction of risk is part of the engineering design process first, and second, we'll discover that we can reduce the risk by spending a certain amount of time, of money, and in that case, whatever we are building, the car will cost us more as we add more risk aversion features in general. All right, so that's very important, very interesting. But then we ask the question now, what is the difference between objective and subjective likelihood? Likelihoods and possible outcome categories, you'll find that depending on the estimation as a probability, that's a measure. You notice that probability, please remember that probabilities have no units, they are unitless. And but sometimes we use a percentage, and that becomes a way of estimating the likelihood or frequency per demand of our operation. We can estimate it per unit outcome. That's why we call this a probability density function, right? So it's a probability per outcome. The frequency is simply per unit outcome. Ratio is during a time interval. And we can simply use a verbal expression per mile travel. For instance, the number of deaths from airplanes or cars per miles driven in society in general. What I want to conclude today is, what are the conditions for the existence of risk? Risk does not exist just by writing a number. They exist under certain conditions. And I have already mentioned them in going, but I want you to remember those, because if you come up with a number as an estimate of a risk, if they don't satisfy their condition, They are not risk. They are something else. First, we said that there must be uncertainty. Oh, here is a normal distribution. The risk here can be reported as the mean value right here, but it is associated with the spread, the uncertainty, the standard deviation, or the normal distribution, or the log normal distribution, or the Poisson distribution, or the Weibull distribution. This is all distributions in statistics. A special case is that a situation with two opposite outcomes with equal likelihood may be, in fact, the most risky one. When you flip a coin, that's the most risky way of determining an outcome. And if the future outcome is known, then n is equal to 1, then you have something that's guaranteed to happen. It is no risk at all. No risk. That's some kind of an accident, maybe. The other condition for the existing of risk that we have to think about is the anonymity of the victims. When there is risk, the victims should be anonymous. That is some kind of agreement among ethicists and professional societies like American Nuclear Society, the American Society of Mechanical Engineers, and so on. I give you an example here, but there is a third condition for the existence of risk that I would like to describe, that the victims should be anonymous. You cannot, for instance, send somebody and knowing that his activity is going to cause his death. So in that case, the risk should be distributed over a large population, and the victims should be anonymous. If the victim is not anonymous, if you send somebody to certain deaths, it is a crime. All right. So in that case, we'll have to cover a chapter on ethics and professionalism, because again, in the risk assessment, you'll find that the ethics come as an important part. So let us remember then that risk is always associated with uncertainty. It is always anonymous. And in that case, it is considered as a risk. So the uncertainty, the anonymity of the victims, and the third condition, you have to predict it before realization. Once the risk occurs, it is an accident. It is not risk anymore. All right, thank you for your attention. I'll stop at that for today. I welcome any question that you have. Alvaro, can you come here, please? Last time, we recorded only 8 seconds. And I had to generate the whole lecture. And let me see here. We have to stop the recording here.